Morning, everyone. Welcome to the last seminar of this calendar year, not the academic year. Seminar will be given by Rose. For those who have not noticed yet, Rose is working with us since October-ish as a project coordinator, and hopefully happily. So Rose did her master at the University of Bristol, if I'm not mistaken, in the UK. And then she moved for a PhD to Brussels, the University of Brussels. And I want to say that she did her PhD there, but not quite yet. I think Rose is in the writing mode right now, so good luck with that, Rose. And today she will be talking about the neutrino detector, and for those who wonder, like I did, it's Rose there, okay? So the floor is yours.
Thank you so much. Yeah, so thank you so much for the opportunity to come and present my PhD, a little bit of my PhD research here at the Cairo 11. So I want to start off by looking at ways that we observe galaxies. So I think you're probably all very familiar with this kind of picture of the Milky Way in lots of different bands of the electromagnetic spectrum. And all sorts of different features can be seen. Obviously, you have the galactic plane in almost on all of these images, but then in high-energy gamma rays, you have these other very bright sources, and in the radio, you have other radio sources at the far reaches. Now, this is a very interesting picture. We've learned lots about the Milky Way and other galaxies using electromagnetic spectrum. But what I want to introduce you guys to is to one of the newest players on the scene in astronomy, and that's neutrinos. So this is neutrino astronomy, and this is the first view of our own galaxy in neutrinos. And this was first published earlier this year. And as you can see more features of the galaxy in this image. So you can still see the galactic plane, but then you can see we have some other neutrino hot sources somewhere in the galaxy. And as we get more and more data, we can learn more and more about what's happening in our own galaxy. And then we can also look at other galaxies further away to see what's happening and what processes are going on in those galaxies as well. And what this leads to is sort of our era of multi-messenger astronomy. We can look at all sorts of different ways of observing the universe, observing processes that are happening in our universe through gamma rays, through neutrinos, and through cosmic rays. Not mentioned here are obviously gravitational waves, which are another very new multi-messenger source. But all of these different things have their own advantages, disadvantages, and I want to focus today on neutrinos and a little bit on cosmic rays. Neutrinos, and specifically ultra-high energy neutrinos, are an incredibly valuable source of information about our universe. They don't get attenuated, or very unlikely to get attenuated in gas and dust between the source and the detector, because they don't interact very often. They have a very low interaction cross-section. And they're also electrically neutral, so unlike cosmic rays, they don't get turned around in magnetic fields in galaxies or between galaxies. And so they point back to their sources very, very efficiently. And so if you have neutrinos, you have a very good measure of the activity that's happening in your source, and also where your source is, which can be very, very interesting. And of course, there's all sorts of things that you can study with neutrinos. The things that we often talk about with ultra-high energy neutrinos, so we're talking neutrinos above 100 gigaelectron volts to sort of a few petaelectron volts. We're thinking about AGNs, blazars, GRBs, and compact object mergers. And obviously, with all of these different types of sources, you have complementary gamma ray observations or gravitational wave observations that you can try and match together and create a picture of what's happening in the universe. In addition to this, you can do a lot of physics with the path that the neutrino takes to Earth. So in addition to all of the source physics and this point source analysis that you can do, you can also have a look at sort of more general cosmogenic neutrino models. You can have a look at what we call the GZK limit, which is a theoretical upper limit to the neutrino or cosmic ray energy in the universe. You can also have a look at neutrino oscillations, and then of course, everyone's favorite dark matter physics. Try and investigate what's going on outside our galaxy. So having sort of given you a bit of a picture of what's happening in multi-messenger physics, I want to come back to this image again with this neutrino picture of our galaxy, sorry. And what are we actually using to make these measurements? What is detecting these neutrinos? What is the instrument that has produced this image? And that is IceCube. IceCube is the world-leading high-energy neutrino detector. It is an amazing feat of engineering. It is a kilometer-cube instrumented ice in the South Pole and Antarctica. It's buried, they drill 3 kilometers into the Antarctic ice sheet and instrument the bottom 1.5 kilometers of that. It costs $300 million, but it is an incredible instrument that is very densely instrumented with 5,160 different optical detectors, which are these eyes, essentially, that look into the ice and look for neutrino interactions that are happening in the ice. IceCube is an incredible instrument. It was completed in 2010, and first major result was the diffuse astrophysical neutrino flux in 2013. Its first transient source was this blazar TXS, which was coincident with a gamma ray observation in 2017. And then this year, we've had 2 major developments in the astrophysical neutrino picture with our first stable sources. So our first AGN outside of the Milky Way, and then obviously the galactic plane. And so in 13 years, IceCube has taken neutrino astronomy from nothing, or a single supernova in 1987, to we can see galaxies, and we can see processes that are happening in the universe, and we can start to investigate the processes that are happening in the universe with neutrinos. So I said IceCube is very nice, very good at this, but how does it actually do that? Well, first we have to look at neutrino interactions, and I'm going to specifically focus on neutrino interactions in ice. Ice is an incredible material with which to detect neutrinos. It's very widely available on Earth currently. It's very dense, and so neutrinos have a much higher chance of interacting in it due to their low interaction cross-section. And it also has some really nice properties in terms of the emission that is created in neutrino interactions. So what happens when a neutrino comes in into our ice, it interacts, it creates this enormous cascade, or enormous, I say, it's tens of meters long cascade of secondary particles that has hadronic or electromagnetic components. And it is an incredibly dense, electronically dense cascade. So you have on the order of 1 billion electrons per centimeter cubed per PeV of energy. So if you have a 1 PeV neutrino coming in, you have a billion electrons in every centimeter cubed of that cascade. So these are incredible properties that make it really useful to detect. What this also gives it is a lifetime on the order of tens of nanoseconds. This heavily depends on the ice properties, because if your density increases, you're going to get a denser and shorter cascade. But what we say is about 10 to 60 nanoseconds is our range. And then these particles in their travel through the ice are traveling at relativistic speeds. So they're going to produce Cherenkov emission in the ice. And what they also produce is something called a Scarian emission. And so give you a little refresher on Cherenkov emission and explain what a Scarian emission is. Cherenkov emission is obviously when charged particles travel through the ice at faster than the speed of light in that material. So in ice, faster than the speed of light in ice. And so this results in an emission of ultraviolet or blue photons. So this is sort of in the optical range. A Scarian emission is a separate process. It's actually due to electrons from the material being dragged along in the cascade that's happening, and meaning that you have more electrons than positrons, or more negative charge than positive charge in your cascade. And this evolves over time. You have a variation in the number of positive and negative charges in your cascade. And so this evolution of the charge excess results in emission of radiation in the radio range. So you have these 2 different methods of trying to detect a neutrino interaction that's happening in ice. what does IceCube do? IceCube uses Cherenkov emission. And this is a couple of event displays from IceCube. So these are the strings. There are 86 of them. And then vaguely you can see the little gray dots that are each little detector module of IceCube. And there are 5,160 of them. In these displays, the size of each of these other circles is also one of these detector modules that has detected some photons from the Cherenkov emission from a neutrino interaction. And the size represents how many photons it's detected, and the color represents the time. So red means it's arrived earlier, and blue or green means it's arrived later in time. And what you can see here are the two main event topologies of IceCube. So you have on the left here, you have your tracks. So you have a neutrino interacting in your IceCube here and moving. A muon moves this way after the interaction from the neutrino charged current interaction. And this produces a really clear path as the muon carries away a lot of the energy of that interaction. And what this gives you is it gives you a really clear direction reconstruction, but a really bad energy reconstruction. So you can find, this is really useful for pointing. You can point back to where your source is, but you have a much larger uncertainty on your energy. Conversely, you have what we call a shower or a cascade topology, and this is every other type of interaction of every other neutrino other than muon neutrinos, charged current interactions. And this is much more concentrated in one place. So here it starts in the middle here and sort of expands isotropically outwards. And this means that you contain all of the energy of the interaction within the detector volume, but you have a very sort of bad direction resolution. You can't tell so well which direction, maybe it's going this way, is it going this way kind of thing. So you have these different types of topologies, and once you wait long enough, so IceCube had to wait for, I think they did their first publication after 28 neutrino interactions, and that was enough for them to say, we have something. You can create a spectrum. Now, this is a complex plot, so I'll have to take some time to explain. On the left here, you have your flux that's been rescaled by the energy. So this means that if you have a line that's flat, that's actually a power law with e to the minus 2. And then you have your energy on the bottom here. So if we look at the center where we have our neutrinos, we can see that it's approximately flat. So it's about e to the minus 2 spectrum. And it's in the energy range of a few hundred GeV to it's about 100 GeV to several PeV. Now, within this energy range, when you're looking at IceCube interaction events, only less than 1% of them are astrophysical in nature. So IceCube has to go through and search through years and years of data, trying to find 28 events out of several million, including astrophysical neutrinos. You can have atmospheric neutrinos, atmospheric muons, cosmic ray background. It all adds up to mean that we have an incredibly complicated data analysis system. You can also see, if this is e to the minus 2, you have an incredibly steeply falling spectrum. It's obviously not as steep as the cosmic ray spectrum, but you have this e to the minus 2 falling spectrum. And what you can also see here is there are two different event selections. So IceCube utilizes the different types of events that it sees in order to make different limits on the neutrino flux. So here we have the crosses are what we call high energy starting events. So that's any event that starts within the detector and then has either with a muon interaction goes out of the detector carrying all of its energy, or it has a cascade and it contains the energy within the detector. So you have varying levels of confidence on your energy in that search. And then they have the shaded region is purely a muon neutrino search. So that's only using track events. And so you can constrain this sort of shaded region, but no further. So there are lots of difficulties with this. And if we take a look at the flux, we can see that it depends on several different quantities, namely energy, area, time, and solid angle. And so if we want to improve from IceCube, because IceCube is an amazing instrument, it does very, very well. But if we want to improve from IceCube, how are we going to do that? Well, we have to look at what our flux is constrained by in order to make a better instrument. So energy, there's nothing we can do about that. What is produced is produced. The universe gives us what the universe gives us, and we can't change that. So looking at the other quantities, the first thing we could possibly improve is solid angle. There is a maximum solid angle available to us of 4 pi steradians. But IceCube in general has 2 different ways of looking at this. So you can either have what we call upward-going tracks, which is where a neutrino travels all the way through the Earth before arriving at IceCube detector volume, interacting, and then creating an upward-going track. So we can be really sure that this is a neutrino because it's traveled all the way through the Earth. This gives us a view of the northern sky for IceCube because it's at the South Pole, and it limits us to, I think, about 1/3 of the northern sky. So what they then did, so this was their first analysis, their second analysis then said, okay, can we be clever? Can we find downward-going neutrino events that fulfill all our categories, fulfill the fact that they're astrophysical neutrino? So this took a lot longer. This came out, I think, 2 years after the upward-going event selection. But they have to be carefully analyzed, and there's lots of improvements on this analysis technique going onwards, including things like using machine learning to try and better identify these types of events in order to widen your solid angle acceptance. The second way you can second way to improve neutrino detection, just leave your detector running for much, much longer. You can improve your duty cycle. IceCube already has a very high duty cycle. It's almost 100%. And so all they can do is just wait for more and more neutrinos to arrive in their detector and to interact. But we have PhD students who need to get their theses, and you want to keep publishing data. So really, your time is limited, in a sense, by human life and human patience. So not so easy to improve. What we can really do is actually improve our area. We can increase our area of our detector volume by orders of magnitude in order to increase the number of neutrinos that are interacting in our detector. And so currently IceCube is 1 kilometer cubed, and then we can have, if we go 10 to 10 kilometers cubed, so an order of magnitude increase, we don't have to wait as long to get the same number of neutrinos interacting. What this also does is it actually increases the maximum energy that you can see. Because if you have one neutrino interacting per 10 kilometer cubed per century or per decade, the likelihood that you're going to see it in this detector is severely reduced compared to this detector. So higher energies mean fewer of them. So if you increase the detector area, you increase the energy that you can see. However, there is a constraint in that for IceCube, Cherenkov light has a mean path length before absorption of about 200 meters. IceCube strings are about 100 meters separated. So this is to capitalize on this mean path length for Cherenkov light. And so if you want to increase your detector volume by orders of magnitude to 10 kilometer cubed or 100 kilometer cubed, you're going to have to instrument that incredibly densely still, and that's incredibly expensive in time and money, especially considering that IceCube cost $300 million in the first place. So we have to come up with a different technique in order to increase our detector volume by these orders of magnitude. And so we can make use of the Ascarian emission. Radio emission in ice has an attenuation length of about 1 kilometer. So this means that you can space your detector parts out much, much further, which means that you can instrument much more sparsely, which means you can instrument tens or hundreds of kilometer cubed of material. And in fact, this is what IceCube is doing. This is the current IceCube detector in blue. IceCube has an optical expansion that's happening. It's meant to happen last year, but various delays. And so this is about a factor of 2 increase in detector volume. But then it also has this radio expansion. And you can see that the original IceCube is this tiny little blue dot in the middle there. And this radio expansion aims to do this 10 or 100 time increase of detector volume in order to try and capture as many neutrinos as possible. IceCube is not the only people doing this. In fact, there are lots of different radio Ascarian methods to try and detect neutrinos. Both ARA and RNOG are in fact pathfinders for IceCube Gen 2 radio. And these utilize antennas drilled into the ice. Either you can have very deep antennas, so up to 100 meters, or you can have more shallow antennas. And this is looking for that Ascarian emission. When your neutrino interacts, it's looking for the emission that is happening from that interaction, and then it will be detected by the antennas, picked up, and so you can say you've detected your neutrino. ANITA is an incredibly interesting experiment. It's actually a balloon experiment. So this flies above the Antarctic continent for sort of 50 days at a time until its balloon pops. And it looks for neutrino interactions that happen in the Antarctic ice so neutrinos come through the Earth, interact in the ice, and the Ascarian emission actually emerges from the surface of the ice and then can then be detected in the air by this instrument. So incredibly good, sort of amazing design concept, and it has worked very well. They've published some cosmic ray results, but similarly with everything here, no successful neutrino detection as of yet. And this has been going on for about the last 10 years. So why is this? Why have they not seen neutrinos? Well, it's a passive detection method. Most neutrino detection is passive. You just have to wait for your neutrinos to come along and interact in your ice. But the problem with Ascarian emission and Cherenkov emission, really, is that the emission is really geometrically constrained, and it's concentrated on this cone. And so if you want to detect your Ascarian emission here, you have to be in the perfect geometrical configuration in order for your Cherenkov, your cone of emission, to pass through your antennas. And so this severely constrains geometrically, it's a pure geometrical factor, how many neutrinos you can see. And they quote sort of these amazing detector volumes of hundreds or thousands of kilometers cubed, when actually they're not taking into account these geometrical constraints. The other limitation is IceCube. This is the same IceCube spectrum as before. IceCube stops at about 10 PeV. These Ascarian type detectors don't become effective until about 100 PeV or above. And so you have this region in the middle here that's not really covered, that's still very, very interesting, as it's an important transition region between sort of GRB physics, AGN physics, cosmogenic models. This is an incredibly important area for theorists to come in and tell us what's happening with our data. But we're currently not covering that area of the space. So we need a different technique to bridge this gap. And what is that technique? Well, that is the radar echo technique, which is what we specialize in. So what is this? You have a neutrino interaction happening. You monitor your ice with a transmitted radio. And then you have a receiver monitoring the same area or the same volume, such that when an interaction happens, your transmitted signal is reflected into your receiver. That's essentially the short of it. And so the idea of this is that you can have these things a kilometer apart, because the radio attenuation length in ice is about a kilometer. And you can very sparsely instrument your volume. My one equation in this presentation is, so this is the radar, what we call the radar range equation. So this is essentially what governs everything about this technique. We have a transmitted power coming in. This is our cascade, and it interacts. And then it reflects to our receiver, and we have some received power. When we're thinking about modeling this interaction, modeling this type of detection, our biggest uncertainty is this radar cross-section of our cascade. And so this is where our modeling efforts really heavily lie, is to try and understand this so that we can interpret our data correctly. How do we do this? Briefly, we have two different ways of doing this. We have something called radio scatter, which is a particle level Monte Carlo code. that uses individual equations of motion of all the different particles in the cascade to calculate the collective signal. And then we have MARAS, which is a macroscopic approach. So that uses much more sort of overall governing properties of the cascade in order to determine what its reflected signal would look like. So we've modeled it, we've had the idea, we've modeled it. Does it work? Yeah, it does. It does work. This was the SLAC T576 experiment, where we have here a high-density polyethylene target in place of ice, because it has similar electrical properties, it's a similar density, and it doesn't melt. And so you have your SLAC electron beam that comes in, and this electron beam is about the equivalent of a 10 to the 19 electron volt neutrino interacting. And then you have transmitters outside of the picture here. You have transmitters, and you can see the white lines that are leading to where we put our receivers. And so you turn your beam on, you have your beam off, you take some data, you turn your beam on, you take some more data. So with beam off, you have nothing. Here we have a transmit frequency of 2.1 gigahertz, and for beam on, you can see that there's a really bright excess around the transmitter frequency, which indicates that you're seeing a reflection from the transmitter through the cascade that's happening to your receiver. So we've got the idea, we have models, we have it working in the laboratory. Great, let's go and build the radioactive telescope for neutrinos. And so this is the idea, that we have the same thing. So again, we have a neutrino interacting, and we have our volume being monitored by a transmitter and by receivers. And so what this allows us to do is it allows us sparse instrumentation. It's an active detection method. So we're not just waiting for the Ascarian emission to reach our detector whenever it does. We are actively searching with isotropic radio being emitted. And so this means that we're not as much restricted by geometry. We have a much wider range of acceptance, but also, very helpfully, when we turn our transmitter off, we're also an Ascarian detector. So you can just sit, if you have a much improved duty cycle, because you can just turn your transmitter off if it's not working, if you have problems, if you need to debug, you can just be sitting there as a passive Ascarian detector as well. So what do we expect our signals to look like? Well, if we have a transmitter in the center here with our receiver antennas spread around, and also we have a vertical spread. This means that we have 27 different antennas around a single transmitter, instrumenting about a kilometer cube. So this is the prototype. We end up at a transmit frequency of 100 megahertz. You can see that the signal is very highly concentrated around the transmit frequency. But we also have this spread in frequency and in time that creates a chirp, essentially. And so what this means is that we have really interesting signal properties that make it much easier to trigger on, so that we can use the properties displayed here to have a self-triggering system. And so if we were to build this, what does it look? Well, how do we compare to everyone else? We do really well. We are very, very competitive with everything. This is a very busy plot, I understand. So this is IceCube, the current IceCube spectrum. This is what it's predicted to carry on if we just leave IceCube running. IceCube Gen 2 is this purple line, and you can see that RET-N with this red line very well matches the current plans for IceCube Gen 2 radio, and Gen 2 and Gen 2 radio. My favorite thing about this plot is that this is for 10 years of running, but RET has 10 stations, and you saw how big IceCube Gen 2 radio was. It's thousands of stations, hundreds and thousands of stations. It's also, if you look down here at this orange line, this is for Grand 200K, which is a planned experiment to be put in somewhere in the middle of China. That's 200,000 different stations for 10 years. And I would think that RET is pretty competitive with that, with just 10. We expect to be this competitive because of those really nice really nice radar signal properties that allow us to trigger very efficiently and allow us to dig out our signal from the noise very, very efficiently. So, great. Let's go and build the radioactive telescope for neutrinos. But does it work? We've proved that it works in the laboratory. The idea works in the laboratory. We have all the models. We have all the ideas. But actually, what we found from, or what we've seen from other neutrino experiments is they've done too much too quickly. They've gone too fast. They've gone straight for neutrinos. And so what we wanted to do as a collaboration is actually put a step in between. And that's this, and this is what I concentrated on during my PhD work, is actually the Radar Echo Telescope for cosmic rays. And so this is a test, this is a pathfinder of the method and the whole experiment, but using cosmic rays as an in-nature test beam. So when I talk about cosmic rays, what am I talking about? I'm talking about charged particles. Typically, I'm talking about protons. There are other species, but I'm usually referring to protons because they're simpler. They interact in the Earth's atmosphere, and they create this extensive air shower of secondary particles, millions and millions of particles that spray towards Earth's surface. The interactions create both hadronic and electromagnetic components. And you can see here the sort of shower development. So this in red is the electronic component. And you can see that it has a point where you have the maximum number of particles alive at any one time, and we call that shower maximum. And then you can also see that this electromagnetic component for this particular shower vastly outstrips the number of number of hadronic and muonic components of the shower. So this is a really they're not insignificant by any means. There's active research going on into why they don't match the models, but the electromagnetic components are very significant. And so we can detect these showers on the Earth's surface using the particles themselves. We can also detect them using radio emission. How do you do that with cosmic rays? Well, there are two ways that cosmic rays produce electromagnetic emission. The first is geomagnetic. So this is just the separation of positive and negative charge as you go due to the Lorentz force of the Earth's magnetic field. And so this creates a time-varying transverse current, which creates radio emission. And then we have our old friend, the Ascarian emission, again, which is the same as in ice, but this time for cosmic ray showers in air. And so you have these electrons dragged into the shower. It creates a charge excess at the front of the shower, and then this time-varying charge excess creates radio emission. And so using these different techniques, using the particle techniques and the radio techniques, we know what our cosmic ray spectrum looks like. This is very, very well defined through many different experiments using a range of different methods so that we can very reliably say this is what the cosmic ray spectrum looks like. But what I want to sort of highlight is the comparison between the neutrino spectrum and the cosmic ray spectrum. For an equivalent energy, so say 10 to the 8 GeV here, we have at least 2, if not 3 orders of magnitude more cosmic rays than we do neutrinos. So purely from a numbers standpoint, if we look at equivalent energy, even if you say that we need 10% of the cosmic ray energy to represent a neutrino, you have orders of magnitude more cosmic rays than you do neutrinos. And what this means is that you can collect the equivalent of 10 years of neutrino data in one summer of cosmic ray data. And so you can use this as a way to really test your technique. But you say, we're looking at interactions in ice. How are we going to test an in-ice interaction using an air shower? Well, actually, if you have an air shower that impacts a high-altitude ice sheet, you get an in-ice cascade. And this is because you interrupt your shower development at or roughly close to shower maximum. And so you have a very large number of particles alive in your air shower that are then slamming into this ice sheet. And what this means that at about 2.4 kilometer altitude, you get 10% of your primary energy deposited into the ice within a radius of about 10 centimeters of your shower core. And this creates a secondary in-ice cascade, which really well mimics the properties of a neutrino-induced cascade. And so, if you can instrument your ice similarly to how you would do it for the neutrino, you can detect your air shower on the surface and then use that to trigger your in-ice radar. And so you can look at your properties of your in-ice shower, compare them with your air shower, and have a good idea of what you're looking at, when you're looking at it, and the fact that there is actually something in your detector. And so this is the governing principle behind the radioactive telescope of cosmic rays, is using cosmic rays as this in nature test beam to go and look for sort of pseudo-neutrino signals in your ice. So that's great. We went and did that. We went to Summit Station in Greenland. It is 3 kilometers in altitude. It is very radio quiet. In fact, we are next to we're actually next to RNOG, which is one of the other neutrino experiments, and it has great facilities and support. And so we were able to go and build this experiment there. And so this is the radioactive telescope for cosmic rays. This is where we are in Greenland. This is Summit Station. And then, so Summit Station is the middle of nowhere, and we are 5 kilometers from the middle of nowhere. And so here is where we built RET, and this is sort of the representation of what we built. And so in the center, we have our transmitter. This is what's broadcasting our radio into the ice. And we have a phased transmitter of 8 different antennas. And what this means is that we have incredible control over the frequency. We have incredible control over the frequency, but also steering. We can steer our beam in zenith angle. It's azimuthally symmetric, but we can steer it so that we lose very little to emergence from the surface or sort of leaking below into the ice below our detector. And so that's in the center here. And then we have 3 receivers here outside at a 30-meter baseline in order to detect the reflections from the transmitted signal. And then we have 3 surface stations. These surface stations are what trigger our detector. They consist of 2 scintillators that form a coincidence, and then a radio antenna so that we can get the radio signal and make a reconstruction of our cosmic ray. And so this whole setup was built, and you might ask, why 30 meters? You said it like it could be kilometers. Well, actually, where we are in Greenland, we're drilling very shallow. We're in the very top layer of the ice. When we're talking about kilometers of attenuation length, we're talking very deep ice that's very, very clear and very, very uniform. In the very top layer of the ice, the ice is very irregular and unpredictable. And so we make the array smaller because this is just a test array. This is just to test the concept. And so we want to ensure that we see the signal that we want to see. So we make it smaller. It also makes it easier to deploy because working in Greenland is incredibly taxing and incredibly hard. So so this is what we did in May of this year. And this is what it looks like in the surface. This is me for scale. So of course, a lot of our stuff is buried beneath the ice, so there's not much interesting on the surface to see, apart from a lot of flags that mark where all the bits are. But we have the flags for our receivers. We have our surface stations where you can see the antennas and the power supplies. And then we also have all of our central infrastructure. So this is an autonomous station, so we have to have solar power, communications, and everything to do with that. So who do you need? Now starts the picture bit. So who do you need to go? You need a team of 5 people, it turns out, is a very good size number of people. So this is our team that went. You need a lot of warm clothing, a lot of snacks, and a lot of heat packs, would recommend. So this is the deployment. And so the first thing you do in your deployment is to ensure that your station will be autonomous. And you do that by building your solar array. And so we built this. We had 3 of these panels that we built and beautifully laid out, ready. And then a storm came in. And so 24 hours later, we went back to our site, and we had this. So you had to spend the next hour digging them all out so that you could raise your solar array and have power out at the site. But once you've dug everything out, you have your solar array here. And then this powers everything. And so you can have your Wi-Fi communications. This looked back to Summit Station so that we could transfer data continuously back to Summit. So once you have your infrastructure, obviously one of the most important parts of RET-CR is the in ice. It's in ice. So you have to drill. So we have a Kovacs coring drill. It's originally designed to taking ice cores, but it works quite well for our purposes as well. And so you can do this, you can use a T-handle, which is a lot slower but more precise, or you can use, we can use the drill to get very quickly down to about 10 or 13 meters is what we ended up drilling. And we ended up drilling 4 of these holes, 1 for the transmitter and 3 for the receivers. And so you end up with lots of these ice cores, which we then bagged up and gave. There was an ice properties group at the summit at the same time, so we bagged these up and gave them to the ice properties group. So you've drilled your 10-meter holes with your Kovacs drill, and so then you need to start deploying your antennas into these holes. And so this is what one of the antennas looks like for RET-CR. It's about 50 centimeters long, multi-dipole. And you have a cable that's your data cable, and then you have this string, which is what you actually support it on. And then you spend several hours with one of you lowering the string and one of you lowering the cable so that you get your receiver into the hole to the appropriate depth. And that's your receivers. For the transmitter, it's a bit more complicated because that's 8 different antennas. So you have this long snake of antennas here. They're all the same antennas as the receivers, just chained together to form the transmitter. And then you lower this into your transmitter hole. This takes 3 people carrying the antenna itself, and then 2 people carrying the cables. I was a cable carrier. I wasn't privileged enough to carry the transmitter itself. But you have then, you have to lower that into the transmitter borehole. The second most important part of RET-CR is the surface stations, because that's what triggers this whole thing. You look for coincident triggers in your scintillator panels so that you know that you have an air shower, and then you look at coincidences between the 3 different stations to see to make sure that you have a cosmic ray and where the cosmic ray is. It allows you to localize it within your array. And so here we have our stack of scintillators before they were deployed. And then this is what the surface station looks like actually out in the field in Greenland. So you have, this is our radio antenna, it looks a bit like a Christmas tree. And then this is independently powered with a small solar array. The scintillators are separated by 20 meters sort of off the picture, and then we have this small electronics box which collects all the data and then sends it to our central data system. Speaking of the central system, this is our central box. It's buried into a vault, which ended up being a little bit of our demise. But you bury this into a vault to avoid snow being blown into it and snow being blown over it. And this is what contains all of the power amplifiers. So this is what powers the transmitter. And all of our central electronics, all of the receiver data is collected here and then sent to Summit Station. And just really to emphasize the glamour of working in Greenland, this is when you forget that there's a lot of snow and you haven't got a lid that's going to protect your precious electronics. So you have to get all 4 of your colleagues to stand with cardboard over your head to block the wind and to block the snow while you, this is my boss, while you fiddle with the electronics. And then, of course, once you're done, you have a lot of sleep. And you look very pretty while you're doing that. But of course, we've deployed this detector. This has happened in May, but what do we have since then? What do we have since then? Well, I can't show you any cosmic ray data, unfortunately. That's still in the works. What I can show you is what we do have publicly available, which is something like this. So this shows you our trigger rate as a function of time. So we took about 5 weeks of data before we had terminal issues. And you can see that our trigger rate varies, and the long scale fluctuations are to do with the number of stations that are forming the trigger. So we have this initial phase where we have 3 stations forming a trigger. Then we jump up because we were doing some diagnostic work, so we wanted as many triggers as possible. So we have only a single station. So if one of the surface stations says, I've got a cosmic ray, we trigger the entire setup. And then again, as we got into sort of more stable running, we ran phases of 2 and 3 scintillated station triggers so that we could get as much data as possible. And we had actually a very successful, even though it was a short data run, much shorter than we wanted, we actually had a very successful data-taking run. And the other thing that I really want to emphasize is this. So this shows, you might ask, you have a transmitter that's transmitting radio indiscriminately into the ice. How on earth are you going to see anything in your receivers if you just have a transmitter that's just blasting into the ice? So what we actually do is this thing called carrier cancellation. And this plot shows the effect of second stage carrier cancellation. It has to run in 2 stages because the transmitter is too powerful at full power to be run without any carrier cancellation. So initially we run it at sort of half power. We perform 1 stage of carrier cancellation to remove the transmitter signal, and this is done by using a time-delayed and scale copy of the transmitter signal that's directly plugged into the receiver channel, so it can directly be subtracted. And then once the first stage is run, you can run the second stage, which is shown here, where the transmitter is run at full power, and then carrier cancellation is performed, and you can see that the transmitter signal is reduced to about the level of the noise floor. And so this way you can see the received signal on top of the transmitted signal. Additionally, the received signal has a phase shift. So you're looking at different phases of the signal so that you can still see it. And so what this shows is a reduction of about 50 dBm per hertz for the second stage of the carrier cancellation, which shows that our methods are really successful in doing this. And so what's the current status? It took 5 weeks of data, and so we're working on all the software to analyze all of that, understanding all the diagnostics, searching for the signals. Unfortunately, ironically, in the coldest place on Earth, we overheated. And so we went offline. That was our terminal issue. And so the equipment was winterized and retroed in August. But we do have a second deployment that was approved in 2024. And so that brings me to my summary of hopefully what I've conveyed to you is how we need to develop new technologies to instrument these larger and larger volumes of ice for neutrino detection. The radar echo telescope for neutrinos is a really exciting new idea. But first, the radar echo telescope for cosmic rays needs to be successful and as the pathfinder for RET-N. My final point, I have talked about one very small part of the global picture of ultra-high energy neutrino detection. It's an incredibly diverse and interesting and vibrant field, which I hope this picture kind of conveys the wide variety of things that are happening, and sort of it's an exciting time for ultra-high energy neutrino detection. So thank you very much.
Thank you, Rose, for an interesting talk. Time for questions. Yeah, Pablo.
Hey there, thanks, that was very nice. I have 2 questions. One is, more or less, I'm a stellar astrophysicist, so I think about much lower energy neutrinos. Do they do anything? Are they relevant to these detection methods?
For radio and radar detection?
Yeah.
So low energy neutrinos, well, it depends how low energy you're talking. If you're talking 10 to the 15 electron volts, they will provide a background for this kind of detection method. But with certain techniques, we're able to sort of strip them out. For much lower neutrino energies, they don't really produce enough energy. They don't have enough energy to produce these cascades that we can scatter off. So even if they interacted within the detector volume, which they will, they're just not. The cascades aren't long enough or dense enough in order to provide the correct signal for reflection. And also for Ascarian detection, they don't produce enough radio emission in order to be detected by Ascarian detectors.
Okay, so I guess not for, solar neutrinos, you're talking MEV scales.
Yeah.
So that's completely off the scale.
Yeah, no. These are especially for, these detection methods are active from about 10 PeV. So it's really, that's where the sensitivity really increases. Solar neutrinos are just a bit too low.
Yeah. And the other thing is when you were showing these expansions of IceCube, everything was like expanded to one side only?
Yes. Let me go. Oh, it's quite way back. No, that one.
Yeah. So
Yeah.
Why is
Why?
everything done to just the side?
Yes. So it's purely, I think, based on what currently exists at the South Pole. So here you have IceCube. In the middle is currently the IceCube lab, and then somewhere over here is the Scott Amundsen polar station. So, and then here, I think, is one of the skiways. So it's purely, you can't drill underneath the skiway, and so it's just basic what's there already, what the constraints are by existing infrastructure. But yeah.
Okay, thanks.
Hi, thanks for the talk. So I was wondering, so what I know about IceCube is that on top of absolute neutrino influx, you can also detect neutrino oscillations.
Mm-hmm.
So I was wondering about the Radar Echo Telescope, whether that construction can also do that, or whether it's just solely about the neutrino detection in itself.
So this is, I have to admit, this is not something that we've investigated fully yet. We are focusing purely at the moment on the flux detection because this is where we're struggling with statistics. Neutrino oscillations are obviously studied by a lot more than just IceCube, but even though IceCube is a very good instrument to do that. Off the top of my head, I don't know, but I think this is something that going forward, we're going to need to investigate the possibility for neutrino oscillation studies, and I don't see why not. I don't see why not that there wouldn't be a study on that using RET-N.
Okay, thank you.
Hi, thank you. In one of your first slides, there was a difference between the different topologies of events you could detect, and then there seemed to be a difference between muon neutrinos and electron and tau neutrinos. I was wondering, what is the physical mechanism that is causing these different topologies based on the type of neutrinos that you have?
Okay. So the main reason why there is different topologies is the production of what is produced in these interactions. So obviously in neutral current interaction, there's nothing produced. It's almost just a scattering event, and so the energy is lost through that. And so that's why you don't get any track flying through. The neutrino has lost enough of its energy that it can't create a track through the detector, and also it's a neutrino, so it can't go on to re-interact and create a track. Electrons and tau neutrino and charged current interactions produce electrons and taus. Taus specifically decay too quickly to move through the detector to deposit energy. There's actually a third topology that I didn't mention that is specific to tau neutrinos, which we call the double bang, which is the first tau neutrino interaction creates the tau. The tau travels a little distance and then decays, and so you get this. You get a double peak in the light curve of a particular optical detector, and they've detected a few of them so far, but they're very rare. Electron neutrinos they interact too quickly with the rest of the material. They lose all their energy in the ice through interactions within the ice, whereas muons are able to receive a lot of the energy from that first interaction. They carry away a lot of the energy, and obviously they're a lot longer lived than taus relatively. So that is purely a function of the energy they possess and the lifetime of the muon that enables them to carry this energy and fly through the detector and create a track.
We have time for one more question.
I'll stick to one question. So in the cosmic ray energy spectrum, you have certain features like once you go across the energy, you have a knee, and then at the bottom you have an ankle and a toe. I know these names are a bit strange, but do you, given that you said that you're in this special range at the PeV range where you transition from what IceCube can see to what you will see in these other detectors, do you think there will be a similar change in the spectrum shape or properties? Because I guess at this same energy range, you will also transition from different astrophysical sources, and also your background will change because your atmospheric neutrino background will start decreasing, and you will maybe get some more astrophysical AGN or other sources that will pick up.
Yeah, that's exactly what happens in the cosmic ray spectrum. So unfortunately, this is not the best plot to demonstrate that because it's not a cosmic ray flux spectrum. Ooh, I might have one actually. No, it's right at the end of my backup. I'm not going to slide. But what you can indeed see that you start to see there is like a break here, which they call the knee. Then you have the ankle. You also have a second knee. They've run out of names because they named it the knee and then the ankle, and then they found a second knee, and then they found an instep. So they're just going through the leg. But yeah, that's exactly what happens. So around the knee, second knee area is the transition between what they think is galactic and extra-galactic cosmic ray sources. And this is actually exactly the area where RET-CR, the red cosmic rays, is sensitive, is this transition region. So yeah, there's really important physics studies going on there, and hopefully RET-CR can contribute a little bit to that.
And so for neutrinos, I guess there will be similar kinks and bumps in the spectrum.
Yeah.
We know you're near there yet because
that
T-bars are way too large.
Yeah, that's one of the things that something like RET-N and Ascarian detectors are really trying to probe is this transition. We do expect there to be, we have some hints, I think, at the end of the IceCube spectrum that there's a little kick up. It's very, very tentative. But there is this sort of expected to sort of come down and then do a little bump due to cosmogenic neutrino generation. Yeah.
Thank you.
All right, I think we are at the hour, and in the seminar shadow, I use the color code to group the topics, the seminars by topic, and I just realized that the color code I gave to your seminar was astroseismology. So I suggest we thank Rolls again for the one of the most unusual seismology talks ever. Yeah? Okay, thanks everyone. We go on holidays for the seminar series, and we reconvene on January 11th with the talk of Germain. Thank you.